if you build an AI workflow, right, with 5 steps, and every single step gets a solid B grade, like 85% success rate, your whole system is still going to fail more than half the time in the real world.
Oh, yeah. It's completely brutal because when you take those 5 steps and you chain them together, that 85% success rate, it compounds downwards.
Right.
So mathematically, 0.85 to the 5th power, well, that leaves you with just a 44.37% system reliability.
Wait. So if I hire an employee who gets things right 85% of the time, the business doesn't just collapse.
No, of course not.
Why is an AI so fragile that a B average literally translates into a coin toss?
Well, because in a live production environment, I mean, you aren't dealing with a clean sandbox anymore.
Right, yeah.
You've got dynamic user payloads, API rate limits, and schema drift, which is, when the data structures your app expects suddenly change without warning.
Oh, I hate when that happens.
Right. And that friction compounds with every single hop. But this mathematical collapse, it isn't just bad luck. It actually stems from 3 very specific architectural failures that the source material points out.
Okay, so what actually causes this downward spiral? Like, what's the first one?
So the first major culprit is what the source calls context contamination. This is what happens when developers take a massive shortcut and they just dump the entire raw conversational history and all the previous tool data just right into the model's working memory.
I'm guessing that creates some severe attention dilution.
Exactly, yeah. Large language models, they process language by assigning mathematical weights to different parts of a prompt, right, to figure out what's most important.
Right.
But when you flood that context window with raw logs and previous outputs, those weights just scatter. The AI mathematically loses the signal.
So it just gets distracted by its own baggage?
Pretty much. And when it gets distracted, it starts to hallucinate schema parameters.
Oh, wow.
Yeah, so basically guessing the wrong data formats or it chooses entirely wrong tool branches altogether.
So if the AI is drowning in its own context, what happens when developers try to solve that by just, I don't know, throwing a bigger, smarter model at the problem?
Oh, that's when they run headfirst into the second failure, which is latency compounding.
Okay.
A lot of engineers will use these massive, 70 billion parameter models just to route basic decisions.
Like what kind of decisions?
Like using an LLM to decide if a user needs the billing department or the password reset page.
Oh, God.
And doing that adds anywhere from 800 to 2200 milliseconds per hop.
So using a massive model just to route a password reset is like, it's like hiring a world-renowned philosopher to work in your mailroom.
Yes.
It's just incredible mathematical overkill.
It is, and it completely shatters your service level agreements because you're adding seconds of pure latency before any actual work even gets done. And worse, when that overloaded philosopher inevitably outputs malformed data, developers usually rely on the third failure.
Which is?
Unbounded retries. They just send the original prompt, the failed output, the error message, and a try again instruction just right back into the model.
Which is exactly like feeding quarters into a broken vending machine.
Exactly.
You're just exponentially burning tokens and, well, eventually triggering HTTP 429 rate limits, right?
Yeah.
Which means the server just completely cuts you off for asking too many times.
Yep. And then the entire pipeline just freezes.
Okay, so if the LLM is this slow, easily distracted philosopher making really expensive mistakes, how do developers actually get it away from the steering wheel?
Well, that's where the Deterministic-State Agent, or DSA architecture comes in.
DSA, okay.
Yeah, the core philosophy of this deep dive source material is to completely decouple orchestration from generation.
Oh, interesting.
You let rigid deterministic code control the flow, and you isolate the LLMs exclusively for scoped semantic transformations.
So what does that actually look like in practice?
Well, it starts at the front door with a FastAPI Gatekeeper. This is basically a lightweight API layer that strips out prompt injection markers and enforces strict data types, all before the LLM ever sees a single token.
Okay, but the real shift is how you handle routing,
Yeah.
right? Because how do you route decisions if you can't use the LLM?
You use math, specifically vector cosine distance.
Oh, okay.
You convert the user's intent and the target tool's purpose into mathematical coordinates. So think of it like plotting 2 concepts on a graph.
Right.
If the distance between them, which is the tau value, is less than or equal to 0.18, it means they are highly aligned.
Okay.
And when the math hits that threshold, deterministic code routes the request instantly.
So millisecond routing instead of multi-second delay.
Exactly.
That definitely solves the latency. But what about the context problem? Like, how do we keep the AI from getting distracted?
For that, you use isolated subagents. Instead of feeding them the whole chat history, they only receive task-specific context.
Oh, I see.
And instead of appending raw text logs as they work, they compact their execution state into JSON diffs.
JSON diffs, right. So that just means they save only the specific data values that change, rather than, rewriting the whole file.
Exactly, which keeps the memory footprint incredibly small.
Wait, hold on. If deterministic code completely controls the flow and we're just updating structured JSON, aren't we just building a traditional web app with an expensive spell checker attached?
I mean, it might look that way, but that restriction is literally the only way to scale securely in the enterprise.
Really?
Yeah, because even a perfectly routed subagent with a clean prompt can still hallucinate a highly dangerous command. So the pipeline absolutely needs final physical boundaries.
Right. Guardrails to keep the AI from casually deleting your entire database.
Exactly.
So if you're an engineer listening to this, you're probably wondering how to actually build those walls.
Well, the first is namespace isolation. This means setting up walled-off, temporary memory for each specific tenant. So there is zero mathematical chance of cross-tenant data leaks.
And what about the broken vending machine problem? How do we stop those infinite retry loops?
Hard circuit breakers.
Yep.
You set the maximum number of schema validation failures to 2.
Just 2.
Yep. If the AI fails to format the data correctly a third time, the circuit snaps. It's a hard stop that routes immediately to a human fallback.
Oh, wow. Which completely prevents those exponential token burns.
Exactly.
Okay, so we've isolated the memory and stopped the infinite loops. But how do you physically prevent the AI from breaking the database itself?
Deterministic write locks.
Okay.
The AI is physically stripped of direct database mutation rights. It cannot touch the database under any circumstances.
Wow, okay. So what can it do?
All it can do is emit a mutation proposal that gets vetted by an open policy agent, or OPA.
What exactly does the OPA do?
It's an external rule engine. It checks the permissions, data types, and logical soundness using strict code, not AI. So it ensures that the action is totally safe before it ever commits to production.
So the AI is basically the enthusiastic intern drafting a pull request, but the deterministic code is the senior manager holding the database keys.
That is a perfect way to put it, yeah.
By the way, the source has an architectural blueprint download of all this, which is incredibly useful if you're trying to build this out yourself.
Yeah, you should definitely check that out, because ultimately all of this architecture points back to the golden rule of enterprise AI, which is do not let AI control the system, let engineering control the AI.
That is the core takeaway. And, it leaves us with an interesting thought to chew on.
Oh, yeah.
Yeah. If our most advanced, multi-billion parameter language models require such aggressive, mathematically rigid guardrails just to survive a basic 5-step workflow,
Right.
how far away is the dream of truly autonomous AI agents that can safely manage their own logic?